First of all, we need to understand what crystal growth is. So suppose we have different nuclei like this. We have different nuclei like this. Now, due to some reason or due to some procedure, let us consider those nuclei come closer and closer and make an aggregate in a regular manner. Then we call that crystal. We call that crystal formation, right? So it is the process where a pre-existing crystal, these are crystal seeds, okay, becomes larger as more molecules or ions added in their positions in the crystal lattice, or a crystal is developed from the solution or vapor and further growth is proceeded. So a pre-existing crystal will be there. According to the definition, a pre-existing crystal will be there, and different other molecules or ions from vapor or solution comes there, and they take their respective crystal lattice point. Then the size of it will keep on growing, and a crystal will be formed. A crystal will be formed, and that is processed further. That's called crystal growth. Now let's move forward. Now we need to understand about characteristics of a single crystal growth. So what are the characteristics of a single crystal growth? I'm going to explain 7 or 8 characteristics over here. Let's understand what are them. So the first one is, okay, it is an irreversible process. That means the crystals once formed cannot be reversed back to its original constituents. Atoms, molecules, or ions in a crystal lattice are trapped, hence they are fixed and cannot move from their position. So, when some atoms or ions come near to the pre-existing crystal, then they are trapped and cannot move at all. Okay, the atoms, molecules, or ions arranged into the correct lattice position, that is Brevis lattice. So they will be arranged in a correct lattice position in some geometrical form. A particle is joining the lattice at the point where its energy will be minimum. So let me explain this point with a diagram. You can see over here, I have put a picture over here. These are all the atoms or ions arranged at their crystal lattice. Now this red one, you can see this red one, the red atom or ion that is in cubic form now wants to go from here to, it can take any of the position, right? Suppose it could come over on top of this crystal, this atom or this atom. It could come over here, it could come over here, but it decided to come here at this position. So what may be the reason for that? Look at here. So, wait a minute. A particle is joining the lattice at the point where its energy will be minimum, right? Suppose if this atom or particle came over here, then what would happen? One face of this atom and one face of this atom, that is the bottom face, would join, and all the other faces will be exposed, right? Will not have any interaction with anything. The same thing will happen over here. That means only one face will be connected, joined. Now if it comes over here, then two faces, one face and two faces will be joined. Similarly, if it comes over here as well, one face and two faces will be joined. But if it comes over here, then one, two, and this, including these three faces, will be joined. So if three of the faces are interacting with other atom, then it will be stable, its energy will be minimum. You can see over here, I have written it properly in a simple way. The corner of the incomplete top layer, that is the corner of the incomplete top layer, has a minimum energy, because in that position, incomplete top layer, sorry, this one, okay, this one, because in that position it will interact with three neighbors. It will interact with three neighbors, 1, 2, and 3. All other positions on crystal layer have only one or two neighbors. So all other position, this or this or this or this, has only one or two neighbors. So it will definitely try to choose that neighbor or that position where its energy will be minimum, and that being where, and that being this position, because 1, 2, and 3, these three positions or these three faces will interact with three faces of this atom or particle. That will minimize its energy. So I hope you understood this much characteristics. Now let's move forward. So other characteristics are, so the crystal growth technique determines the material's characteristics and also the concentration of impurity and defects. So crystal growth technique can determine the material's characteristics and concentration of impurities. If you already don't know about impurity, you can visit my channel. I've already put a video over there about the impurities in a crystal. Yeah. Now, the techniques are typically based on reducing the solubility of the sample. So forming crystal means reducing the solubility of the sample. The sample solubility will keep on declining as the crystal is forming. Okay. Now, mostly solubility of the compound decreases with decreasing temperature. So if the temperature decreases, then solubility also decreases. We know that from the concept of saturation and supersaturation. If we consider water in a beaker and if we put sodium chloride, then what will happen? It will get dissolved. If more of sodium chloride is added, then a point will reach when the sodium chloride will stop to get dissolved. That is called saturation condition, right? Now if we increase the temperature of it, then what will happen? More sodium chloride will be dissolved. That is called supersaturation condition, right? So we can simply say that in reverse, if temperature is decreasing, then the saturation also, or then the solubility will also decline. Okay, then the solubility will also decline. Hence, cooling of a saturated solution, once a saturated solution is formed and if we cool it, then that often produce crystals. So I've already spoiled it. So cooling of a saturated solution will often produce crystal. That is the process to form crystal. Now, rate of change of temperature determines the size of the crystal. Okay, so rate of change of temperature. So how quickly or how slowly we are changing the temperature, that determines the size of the crystal. Slow cooling leads to a few nuclei and large crystals, but rapid cooling leads to precipitation of amorphous solid or microscopic crystals. So you can see over here, suppose there are many nuclei like this. Okay, now if we cool it slowly, this is a slow cooling, then what will happen? One crystal will be over here, another crystal will easily form over here, another crystal will come and another, sorry, nucleus will come and attach to it, and as a result of that, the size of this crystal will keep on increasing. But if if in another case, if the temperature is decreasing, if a temperature is decreasing in a rapid way, then will these nucleus get enough time to aggregate properly? No. Then a lot of microcrystals will be formed, that is amorphous amorphous solid will be formed. So I have put it over here. So hence, nucleation and growth determines the size and purity of single crystal. So nucleation and growth determines the size and purity of the single crystal. If nucleation rate is slow, but growth rate is fast, larger crystal will result. I'll explain it later in the video. Similarly, if nucleation rate is fast and growth rate is slow, small crystals or even polycrystalline sample will result. So this simply try to say that, see, nucleation simply means, suppose these atoms are over here, these are the nucleus. Now if they come together to form aggregate, that is called nucleation. But if its size keeps on increasing, then that is called growth. Okay, a single crystal growth. Now if nucleation rate is slow, that means if these atoms are aggregating in a slow way, then what will happen? Then the large crystals will be formed. Same crystal will keep on increasing. But if the nucleation rate is fast, if nucleation is happening quickly, okay, more and more crystal is coming over here, okay, then what will happen? The crystal size will be slow, but there will be a lot of crystals.